In my previous videos, I have been explaining the concepts of vector algebra. Now in this video, we will look into some of the problems based on vectors. So the first question is, represent graphically the displacement of 45 centimeters, 30 degrees north of east. Okay, so we have to graphically represent a displacement which is 30 degrees north of east and its length is 45 centimeters. So let's first look at the direction north of east. So this is our north, south, west and east. So north of east would be, this is our east, so north in this direction. So this is our angle. Okay, so this is 30 degrees and the length of the displacement is 45 centimeters. Okay, so similarly, let's do the second one. The second one says 80 kilometers, 60 degrees south of west. So let's again mark north, south, west and east. So the direction is south of west. So you go to west and south of west. So it's here in this direction and the angle is 60 degrees. So you have to measure 60 degrees from here and you mark your vector. So this is 60 degrees and the distance is given by 80 kilometers. 80 kilometers. This is not to scale. This is just for, once you mark the distance here, then it is understood. In the next question, the question says, prove that the relation R defined on the set V of all vectors by A related to B, if A vector is equal to B vector, is an equivalence relation. So you have to prove it's an equivalence relation. So to show it's a equivalence relation, you have to prove three things. One, you have to prove that it is reflexive. Two, you need to prove it is symmetric. And three, you need to prove it is transitive. So let's look at one by one. So we know that vector A is equal to vector A. Therefore, we can say that A is related to A. So it is, the relation is reflexive. Okay. Then let's prove it's symmetric. We are already given that vector A is equal to vector B, which would imply that vector B is equal to vector A. So this would mean that A is related to B, vector A, and vector B is related to vector A. So this means the relation here is symmetric. Then the third, we need to prove that it is transitive. So let's consider a vector C. So let's assume that C be a vector. And if vector A is equal to vector B, and if we can say that vector B is equal to this vector C, then this would imply that our vector A is equal to vector C. This can be shown. So therefore, A is related to B here, and B is related to C, which implies that A is related to C. So this means this is the relation is, you say the relation is transitive. Therefore, the relation R is an equivalence relation. Hence the proof. Okay, in this problem, let A and B be the position vectors of the points A and B. Prove that the position vectors of the points which trisects the line segment AB. So note the point, trisects the line segment AB, which means AB is divided into 3 equal parts. Okay, so AB is divided into 3 equal parts. So when you do that, the points P and Q are defined by A vector plus 2B vector over 3 and B vector plus 2A vector divided by 3. So we already given that OA vector is A vector, OB vector is B vector, and P and Q. Let's consider 2 points P and Q on AB, and let's assume that P and Q are the points that divide AB into 3 equal parts. So let's start out by saying and defining OA vector is vector A, OB vector is vector B. If P and Q are points on AB such that AP is equal to PQ is equal to QB, because we are given that it trisects the line segment AB. So AP is equal to PQ is equal to QB. Therefore, we can define the ratio AP is to PB as 1 is to 2. If AP is 1, then PB will be twice, because it's dividing AB in 3 equal parts. So now, using our section theorem, we can say that OP vector is equal to 1 times of vector B plus 2 times of vector A divided by 1 plus 2. Okay, so our vector OA and is vector A, and vector OB is vector B. Since P is dividing AB in the ratio 1 is to 2, we are multiplying vector A with 2 and vector B with 1 and dividing it by 1 plus 2. So that's our section theorem. So this would mean this is equal to 2A vector plus B vector divided by 3. I hope that's clear. Similarly, we can define the ratio AQ is to QB is equal to 2 is to 1. AQ is to QB is 2 and 1 because it's already given. Right. So again using the same technique. So let's define the vector OQ with the section formula. So now it would be 2 times of vector B. So this is 2 parts, right? So 2 times of vector B plus 1 time of vector A divided by 2 plus 1. So 1 times of vector A divided by 1, 2 plus 1. So that's equal to 2B vector plus A vector by 3. So this is based on the section theorem formula, which is MA vector plus NB vector divided by M plus N if the line segment is divided in the ratio M is to N. Okay, so just writing this for your reference. So we have now proved that the position vectors of the points P and Q are position vectors that trisect the line segment are 2A vector plus B vector divided by 3 and B vector plus 2A vector divided by 3. Hence our proof. Okay, in the next problem, if D and E are the midpoints of the sides AB and AC of a triangle ABC. So we have a triangle A, B and C, and you have D and E as the midpoints of, D is the midpoint of AB, E is the midpoint of AC. Now we need to prove that the vector BE plus DC, vector BE plus the vector DC. So the these are like the points that join the midpoint to the vertex. Both these lines is equal to 3 by 2 BC vector, which is this vector. All right, to prove this, what we will do is we will consider origin O. So consider origin O somewhere here, just for, so, and then let's call this as vector A. Similarly, we will have all the vectors, vector B from OB, OC. So we will be referring to the origin O when we talk about vectors. So let's define vector OA as vector A, OB as vector B, OC as vector C. So these are all position vectors with origin O. Since D is the midpoint of AB, we can say OD vector is equal to, D is the midpoint of AB. So by section theorem, you would say that this OD is equal to OA plus OB divided by 2, which is vector A, vector B divided by 2. So vector A plus vector B divided by 2, because D is the midpoint and divides AB into 2 equal halves. Similarly, we can define OE as OE vector as OA, or we can call it as OA is vector A plus vector C divided by 2. Okay, so next we need to find vector BE plus vector DE. So vector BE plus vector DC can be defined. Now you can define vector BE as vector BD plus vector DE. So vector BE is defined as vector BD plus vector DE. Similarly, we can define vector DC as vector DE plus vector EC, which is DE plus vector EC. Okay, so that's DC. DC can be defined as DE plus EC. And further, a vector BD, which is this vector here, can be defined as half of BA vector, because D is the midpoint of BA. So we can write BD as BA vector by 2. We have DE plus DE, so that is 2DE vector, plus we can write our EC vector as half of AC vector. AC vector by 2, because E is the midpoint, so EC is half of AC. Okay, now further, substituting the values of the position vectors in BA, so we can define our vector BA as minus B vector plus A vector. Minus B, because B vector is in this direction, so minus B vector plus A vector, or in other words, we can call this as vector A minus vector B by 2 plus, and we have our DE vector. Next, what we're going to do is we're going to define this vector DE. Now we know that DE vector can be defined as minus OD plus OE. So I can say OE vector minus OD vector. Okay, so it's very simple. DE vector is minus OD plus OE. So I'm putting it as OE minus OD. Okay, it's just we're bringing everything back to the position vectors. So we have already seen here and here, and let's substitute those values here. So OE vector is vector A plus C vector divided by 2, and OD is A plus B divided by 2. So simplifying this, we can say vector A plus vector C minus vector A minus vector B, so that will be equal to vector C, A and A will be cancelled, minus B divided by 2. Alright, so we're going to substitute this here. So we're going to call this as 2 times C vector minus B vector divided by 2 plus, and our AC vector is nothing but vector C minus vector A. AC can be written as vector C minus vector A. So vector C minus vector A. Okay, so we have replaced all these using position vectors. So further simplifying, I think now it's kind of easy. So let's put a big line and the denominator 2 here, and let's just put all the values on top. vector A minus vector B 2 times C vector minus 2 times B vector plus C vector minus A vector. So A vector and A vector is cancelled. So minus B and minus 2B will be minus 3B, say minus 3B vector. You have 2C plus C, so it's a 3C vector divided by 2. So you can further simplify this as 3 by 2 into vector C minus vector B. Okay, now what is vector C minus vector B? Vector C, okay, vector C minus vector B is this direction, in this direction. So minus vector B plus vector C is nothing but our vector BC. And that's equal to 3 by 2 BC vector. That's what we have to prove, hence the proof. Okay, let's do the next problem now. Prove that the line segment joining the midpoints of two sides of a triangle is parallel to the third side whose length is half of the length of the third side. So here you're asked to prove that if D and E are midpoints of the side AB and AC of a triangle ABC, then you have to prove that DE is parallel to BC. Okay, so before you continue to watch this video, I suggest that you pause it and give this problem a try, because now that you've seen 4 problems, I'm sure that you can try and solve this, and then you can come back. So to solve this, we need to again consider a position vector or a position vector OA, OB, OC with the reference to the origin O. Okay. Now let's define OA as vector A and OB as vector B and OC as vector C in triangle ABC. Alright, since D is the midpoint, of AB, we know now that we can define OD as vector A plus vector B divided by 2. Okay, that's simple. Similarly, E is the midpoint of AC. So we can define OE vector as vector A plus vector C divided by 2. Alright, now we can write DE, because we need to prove that DE is parallel to BC. So DE can be written as OE vector minus OD vector. DE can be written as OE vector minus OD vector. Okay, so let's substitute the values of OD and OE here. So it's vector A plus vector C by 2 minus vector A plus vector B by 2. So further expanding, vector A plus vector C minus vector A minus vector B divided by 2, which is equal to A and A will become cancelled. Vector C minus vector B divided by 2. And we can see that vector C minus vector B is equal to BC vector. BC vector can be defined as vector C minus vector B. Minus vector B plus C will give you BC vector. So substituting, we can call this as BC vector by 2. So we can define our DE vector as half of BC vector. So in simple, you have DE vector as a scalar multiple of BC vector, where lambda is a scalar. Therefore, DE is parallel to BC. Hence our proof. Okay, in the next question, the question reads, prove that the line segments joining the midpoints of the adjacent sides of a quadrilateral form a parallelogram. So let's define ABCD to be our quadrilateral. So ABCD is a quadrilateral. And let P, Q, R, S be midpoints of AB, BC, CD and DA. Next, we can define the position vectors OA as vector A, OB as vector B, OC as vector C, and OD as vector D. Next, we can define our midpoints position vectors. Let's define, say, OP is equal to, since OP is the midpoint of AB, that would be vector A plus vector B divided by 2. Similarly, OQ will be equal to vector B plus vector C divided by 2. And our vector OR will be defined as vector C plus vector D divided by 2. And our vector OS would be equal to vector D plus vector A divided by 2. Next, let's find what is our PQ. Now, PQ can be defined as OQ minus OP vector. Okay, PQ vector can be defined as OQ minus OP vector. So further substituting the values of OQ and OP, that would be vector B plus vector C divided by 2 minus vector A plus B divided by 2, and that's equal to B and B will become cancelled. So you'll be left with vector C minus A divided by 2. Similarly, let's define SR vector. That will be equal to OR vector minus OS vector, and that's equal to vector C plus vector D by 2 minus vector D plus vector A by 2. D and D will become cancelled, so you'll be left with vector C minus A by 2. Then a vector PS. I'm defining all the vectors which are joining the midpoints to the adjacent side of the quadrilateral. So PS would be equal to vector OS minus vector OP, and that would be equal to OS is D plus A by 2 minus vector A plus B by 2, and that would be, we will be left with vector D minus vector B by 2. Okay, so Let's continue to mark the other side which connects the two midpoints, which would be QR, that would be equal to OR minus OQ vector, and that would be equal to vector C plus vector D divided by 2 minus vector C plus B by 2. Solving, you will get vector D minus B by 2. Okay, now let me define this as 1, 2, 3, and 4. From 1 and 2, we can say PQ is equal to SR. They are both equal to C minus A by 2. And then from 3 and 4, you can say PS is equal to QR. They are both equal to D minus B by 2. Therefore, P, Q, or S is a parallelogram. Hence our proof. Okay, in the next question, if vector A and B represent a side and a diagonal of a parallelogram. So you have the parallelogram O, A, B, C, and we are defining A as a side and vector B as the diagonal, because it says A and B represent a side and a diagonal of the parallelogram. Find the other sides and the other diagonal. So you need to find AB, CB, OC, and you also have to find AC, which is other diagonal. All right. So let's define our OA vector is equal to A and our OB vector is equal to vector B. So our AB can be defined as AB can be defined as minus A plus B. So which is B minus A. All right. Then we can define our CB as equal to OA because they are in the same direction and same length because it's a parallelogram. So that would be equal to vector A. Similarly, our OC will be equal to vector AB, and that is equal to B minus A. Next, we need to find AC vector. So our AC vector is equal to AC can be defined as AB plus BC. Vector AB plus vector BC. Our AB is vector B minus A, and our BC is, we have CB which is A. So CB is equal to A, therefore BC will be equal to minus A vector. So this minus A, and that is equal to vector B minus vector 2A. So therefore the sides of our parallelogram are vector A, comma vector B minus A, vector A, vector B minus A, or the sides of the parallelogram and vector b minus 2a vector and vector b or the diagonals of the parallelogram. This will be our last problem in this video, and this is a very simple question. It says that if PO vector plus OQ vector is equal to QO vector plus OR vector, then prove that PQR are collinear. Okay, so I have taken the position vectors PO and OQ and also OR. Okay, now we need to prove that it's collinear, and what's given to us is that PO vector plus OQ vector is equal to QO vector plus OR vector. Now this is given. What is PO vector plus OQ vector? PO plus OQ is nothing but PQ vector. So this is equal to PQ vector. So let's mark this as 1. And our QO vector plus OR vector, QO plus OR is nothing but QR vector. So it's QR vector. So let's mark this as number 2. So substituting 1 and 2 in the original given statement, we can say that PQ is equal to QR from 1 and 2. Okay, so what does that mean? This means that PQ is parallel to QR vector, and you can see that Q is a common point. Q is a point on both PQ and QR. Therefore, we can say that PQR are collinear. That was simple. Thank you for watching Maths Tutorial Anand. Please like and you can comment if you have any questions, and do not forget to subscribe to get more videos like this.